So our next speaker is Anthony Wood from Graphcore, where he's the formal verification team lead. Anthony has held a number of design and verification roles on CPUs, GPUs, and IPUs at Infineon, XMOS, Imagination, and Graphcore. He strives to find ways of improving the productivity of verification engineers, and of course, he agonizes about potential verification holes.
Okay. Yeah, right. So as verification engineers, we spend our time we're making the chip out of doesn't match the RTL we're verifying, then we've got problems, right? So that's what I want to look at here, about these situations that can occur with System Verilog, where you get this disparity. None of this stuff's new, but I haven't seen it all kind of brought together like this. So that's why I wanted to talk about it. Okay, and they are terrifying. They're honestly terrifying, I think. Right, that doesn't do it. Okay, right. Let's let you in gently. So we've got two simulators here, and these commands here will compile, elaborate, and then simulate the System Verilog. And we'll just use their default settings. Now the question here is, do we expect them to give the same output? Okay, well, you know, I'm not wasting your time here. We don't, right? We don't actually expect them to have the same output necessarily. And here, this is running on two of the main three simulators here. We get different results. So what's going on here then? Well, looking at the files, the first file here, it just contains a define. There's just a definition. And then the second file, if that definition is visible, then we fail. And if it's not visible, then we pass. So what's happening here is that in one of the simulators, that define is obviously visible. The content of the first file is visible, and in the other simulator, it's not visible. Right. So this is all the thing we're talking about here is compilation units, and the System Verilog Language Reference Manual, the LRM. This is how it defines a compilation unit. Okay. Compilation unit is a collection of one or more System Verilog source files that are compiled together. And it goes on to say that the exact mechanism for defining which files constitute a compilation unit is tool specific. Compliant tools shall support A, all files on a given compilation command line make a single compilation unit, and B, each file is a separate compilation unit. Okay, so obviously what's happening with these two different simulators is one of them is using A by default, and the other one's using B by default. Okay. Clearly, the visibility of the defines has a huge effect on the logic in the design, right? You'll see in the System Verilog for the RTL that there'll be lots of if-defs and if-end-defs. And obviously, you know, different defines are going to change that logic. Now, if we've got differences between two different simulators, then we can detect that. You know, we can run the two simulators and we can see that one passes, one fails. But the problem I'm concerned with here is that what happens if we do all our verification with certain compilation units in the simulator, but the synthesis and all the backend tool is using different compilation units? I mean, that basically invalidates our verification. So we want to be really, we want to make sure we're not doing that. So how do we do that? Well, when we deliver the RTL, obviously we deliver RTL, but it's critical that we tell our customers being, could just be the back end team in our company, or if we're an IP company, it's our real customers. We need to tell them which compilation units to compile the RTL in. Okay? And then, of course, we're verification engineers. We don't trust they're going to do it. We want to verify that they actually do it. So how do we go about demonstrating that it's really happening, that they are using the same compilation units? Right. Gate-level sims to the rescue. So all of these, for all of the problems I'm going to talk about, gate-level sims form part of the answer for how we go about making sure that that we combat any mismatches between simulation and synthesis. So I just want to say a couple of words about gate-level sims. So really, gate-level sims because we're creating a netlist that's gone through the synthesis flow, that is our opportunity to check the synthesis flow and check that in this case, the compilation units are the same, and we get the same visibility of the defines. So they are very useful. Quite often, though, we have people have a bit of a sort of mental block on gate level sims. It's often considered to be something that you run on like the full chip, and you know, they're very slow because they've all got you know, all the timing information on them, and you could only ever aspire to running just, you know, a couple of hundred simulations. But this just isn't true. Right? We can run a gate level sim on a netlist that's been created down at a low level, down at the block level for your block level test benches. And the other problem is that people think that it's got to be run on a timing clean netlist. You don't need to do that at all. You can just synthesize to primitives, so just the very first bit of the synthesis process. You know, you don't even need to start optimizing at all. So just do the very first synthesizing to primitives. Obviously, that's very much quicker to synthesize, and it's quicker to simulate. And as a side point, if you're used to having problems with gate level sims, you avoid X-pessimism issues if you are running on primitives. But I'm not going to do that again. Right, okay, back to compilation units. Something else that we can do to try and ensure that the compilation units are correct is to lay traps by erroring out elaboration time. So for instance, what you might do is you might put a define in a file, and in another file that you do not expect that define to be visible in, you can error out if it's visible. And you can do the opposite as well. You can put a define in a file, and you can error out if it is not visible, and it should be. Okay, so you can lay these traps, and these will fire in the synthesis tool. Right, final word on defines. Of course, on your command line, you can also issue defines, so you need to make sure that they are the same in your simulation tool and your synthesis tool. I would encourage all those defines to go onto into system Verilog. You know, if you, yeah, that's what I would do. And yeah, you want to make sure that you really understand what all your defines do. Okay, right. Hopefully everyone's warmed up now. On to next issue. This is where we have a genuine RTL bug. This is fine. This is what we deal with all day, every day. The problem, though, is because of the way that the RTL has been written, we cannot detect this bug in verification simulations. Okay, let's look at the code. So all this is just a single flip-flop, right? That's all we're doing here. So we've got an input signal that's registered, and then if the register is set, then we output a 1, otherwise we output a 0, okay? So what's the RTL bug here? Well, it's not reset. There's no reset here. So in that first clock cycle, it can be a 1 or it can be a 0, we don't know. We don't know what's happening. So this isn't the problem though, right? Because we deal with bugs all the time, right? The real problem is, why can't our simulations detect this bug? And the problem here is that condition there. So if the register is set to a 1, we output a 1. Otherwise, we output a 0. Now, if, as it is in the first cycle, the register has an X value, we're going to output a 0. It gets cleaned up. So in real life, in our silicon, this can be a 1. In our simulations, it's going to be a 0. It's terrifying. It's a terrifying prospect, right? We are not simulating the logic that we're synthesizing. And if we run the sim, it passes. Gives us a lovely, warm, fuzzy feeling. But that is misplaced because there's a bug. We know there's a bug. Thankfully, our gate level sims correctly identify the bug and fail. Okay, I hope you can see these. This is the waveforms. Hopefully, you can see that on the RTL sim at the top, you can see the X on the register, and it's cleaned up. It's zeros afterwards. It doesn't propagate. And the gate level sim correctly propagates the X and causes the test to fail. Yeah, this is really bad, very bad. Right, what's the problem here? System Verilog LRM, that's the problem. If simulations are following the LRM, then they do not match the synthesis logic here. And this is a problem known as X optimism, which, you know, I don't particularly like the name because it sounds like a good thing. X optimism sounds like a good thing, right? And it's awful. It's absolutely terrifying. But the good news is we have a solution. All the simulators have got realistic X propagation modes. So what happens in these modes is we throw out the LRM. We try to propagate X's just in the same way that real hardware propagates. And they work. So here at the bottom there, the trace is the, you can see that the X is on the register, but it propagates correctly out in the same way that the gate level sim does, and the test files. So we're able to detect that bug. It's no longer hidden by X optimism. Bad news is that all the different simulators differ on how they simulate in their export modes because it's not defined. The behavior is not defined. The LRM defines how to simulate, but we're throwing the LRM out. So the simulators all differ slightly. But the good news is that they're pretty good at exposing bugs. I think that about 95% of bugs that are normally hidden by optimistic X propagation are exposed by realistic X prop modes. But if you want to expose all of them, then you need to be running gate level sims, and that should get them all. Okay, so you need to run regressions on your normal LRM, you need to run them in X prop mode and in gate level sim. Right, unique cases. Let's take a look at this. So here we've got a case statement. It's got some complicated conditions, and I've synthesized it on the right there. I don't expect you to read that. I'm just trying to show you that there's quite a bit of logic there. So yeah, that's what it synthesizes to. Now the designer has now gone away and they decide they want to change the RTL and they want to put the word unique there, the term unique there. Now, what effect does this have on this on the synthesis? Well, it's dramatic. It's staggering, the effect that has. Literally all of the logic is completely optimized away and we're left with just a single wire. Now why is this? The unique term there says that it is telling the synthesis tool only one of these conditions can occur at once. So in the bottom row you can see E equals 1, and that necessarily means that the three above have to be 0. So Z is always the same as E, and the synthesis tools are perfectly capable of coping with this. So that's why they optimize just to a wire. Okay. Unique cases are obviously powerful, really powerful. You obviously get an area reduction, which is really useful. Obviously, there was a massive area reduction there. You don't get that. You don't normally just optimize all the logic away, but you do get area reductions. And also performance increase. Obviously, you know, signals don't take so long to go down a wire than through the logic. But there's a big but here, right? This is the problem to do with simulation. So here, I've got a test bench. A to D are just 0 for the entire length of the simulation. And on E, we've got a single pulse. Okay, we've just got a pulse on E. Now, remember that Z is a wire driven by E. Okay, so what does Z do? Well, disappointing is an understatement. I mean, that is terrifying. Z is 0, right? It doesn't follow what the signal that we're doing. Right? The synthesis, the simulation is not following what we know is going to happen for our synthesized logic, right? This is really terrifying. Why is this happening? Well, there's an RTL bug, right? Again, we deal with the RTL bugs all day, all night. But the problem with this RTL bug is it messes up our simulator. So the problem here is that B is less than 24,000. So there's two cases there that are valid, and this is what's messing up the simulator. It doesn't know which one to do. The good news is that we get a warning. All the simulators give a warning. Now, just to be clear, that warning is telling us that your verification isn't valid. Right? We are not simulating the same logic that we're going to put into a chip, which is terrifying, right? Don't miss that. Don't miss that warning, right? That's really bad. So this is my checklist for coping with unique cases. Firstly, that warning, you want to promote that to an error. You do not want to hide that. You don't want to miss it. Secondly, there's always somebody who works out that they can, rather than fixing the error, they can turn it off. So don't let them turn off the assertions that cause those warnings. Formal tools, they're useful here. So formal tools will all have a mode where you can load up the RTL and it'll auto-generate some properties. And one of the sets of properties that it does is that they can generate properties to check that your cases are indeed unique. And they're useful. They can definitely find violations. Unfortunately, sometimes they find false violations when the constraints aren't, when you haven't constrained the design, and you probably don't want to put the effort in to do that. Also, sometimes they don't converge, so you can't be sure either way. Gate level sims as well. Obviously, that's useful to do. And discussing these things with your colleagues, right? Just raising the profile of these horrific situations you can get into. Maybe you want to ban them or do something else with them, right? Okay, that's all of those cases. Thanks for indulging me in the things that keep me up at night.
We do have time for a quick question if there is a question. So just one. So one online. So you're suggesting that people just run very small GLS on zero delay.
Yeah. So I mean, not very small. I mean, do it at the same level. Whatever your DUV is, synthesize that and try and use the same synthesis flow that you're really going to be using. Your back end are going to be using. And yeah, it's run the whole regression because there's no point doing just a few.
Should be working.
Quick one. Why not use the linting to check your code? Say, for example, rather than using if statement, you can use case statement and avoid X propagation. So you can link the code and identify such issues earlier rather than just going forward.
So why don't you link the code and check that, for instance, you're not resetting all the registers? Yeah?
No, for example, you can have a lint rule saying designers should never use if statement.
Can never use what? The case?
Yeah, they should.
Yeah, well, that's it. That's something they could do, right? You can have that discussion. You can ban all cases. But of course, don't forget that you can have unique ifs as well, right? Which has the same problem, right? Again, you can do that. It's just having a discussion and putting it into your RTL coding guidelines. Yeah, absolutely. Yeah, do this. Yeah.
Okay, and there's a thing about RTL coding guidelines, which you can then codify in your link tool.
Yeah.
Yeah.
Okay.
Brilliant. Okay. Thank you.